Thank you. It's great to be here. Thank you for all attending. Thanks to the organizers for inviting me. I really like the idea of a conference where different people from different areas meet and exchange ideas, and so far this has been a very pleasant one. I come from a couple different worlds, but I think closest to this group is the world of translation surfaces. And so my main objective is to sort of advertise translation surfaces. You've already seen them in some of the talks, like from Vincent Delacroix and from Sam Friedman. Even the director of the CERM is interested in translation surfaces. There's some representation here, of course, but I know that many of you maybe never saw one before you came to the conference, so please don't assume that I'm assuming that you know what they are. We'll get to them. But I have some I'm basically, my first thing I want to do, like Peter says, we want to sell something, and I want to sell translation surface to you, maybe as a data structure if you're a computer scientist. And the other objectives I have are the following. Well, the outline is the following. I want to look back at Delaunay's empty sphere method. So that's step one. Step two, I want to look at the special partitions. This is Delaunay's word. So of course, it was in French when he wrote it, but and the special partitions actually lead to a tessellation of the hyperbolic plane. Okay. And then I want to talk about a generalization of this observation to translation surfaces. And then I want to consider the reconstruction problem. And I used the word reconstruction because at lunch someone told me they were a computer scientist who was saying that they didn't feel very, didn't understand what we were trying to do. But in many cases, what we're trying to do is reconstruct things. And so you start with some data structure, you want to reconstruct another one. And that's what basically this map is doing. There's a map that takes special partitions to a tessellation, special Delaunay partitions to a tessellation, and the question is whether the question I want to get to is, given that tessellation, can you reconstruct the surface? In particular, can you reconstruct? So you want to do an inverse map. So those are the things I want to do now. I'm just curious, who this now audience participation, who knows Delaunay's empty sphere method? 1, 2, 3, 4, 5. Good. Okay, so those, and who's a computer scientist? Okay, good. So the computer scientists may know this, and I'm not sure the mathematicians know this method, the original method, right? So it's not a very good algorithm, I don't think. I mean, in terms of computers, but it's the original thing. And then who knows what a tessellation is? Okay, good. So that's yeah. So if not, then you should go and look up Escher circle and see demons flying and stuff like that, right? Tessellation of hyperbolic plane, right? The circle limit theorems. Good. circle limit pictures. And then translation surfaces. Who knows what a translation surface is? Oh, this is wonderful. I don't need to, I'm done. Everyone knows that. I mean, you guys all know everything. And then, well, anyway, then we'll get to this. So good. So that's good to know. Okay, so let me start with the empty sphere method. By the way, it's a very weird spelling. It's Delaunay. Normally, you see this as D-L-O-A, this guy. And so I was like wondering what the heck is going on when I saw. So the paper about Delaunay, the first paper about Delaunay partitions is written by that guy. And I went, ooh, there may be some relationship between these people. And of course there is. That's sort of the Russian spelling, or I don't know what they do in Cyrillic. I don't know how to spell in Russian, but apparently that's how the Russians would transliterate it. Whereas this is a French word, a French spelling, say. And in fact, so if you look on Math Tutor, what is it, the history in Scotland, whatever, there's a site where you can see all the biographies of different mathematicians. And you can look him up, and he's got a page, and it says there that in fact he was related to the guy who was in charge of the Bastille in 1789. I guess it was July 14th, and was one of the first victims at the Bastille, and that was his ancestor. And in fact, it turns out that's false. Totally false story. But it is true that his great-grandfather did go to Russia with Napoleon, I guess, and then was captured, and he was sent to a prison camp. He eventually made his way back to France. But somehow along the way, he fell in love with some Russian aristocrat, a young woman. And then he went back to Russia, his great-grandfather, and they got married and had children, and there's Delaunay. So the original name was this, of his great-grandfather. So anyway, he was also a very interesting guy. He was a mountain climber. He has a mountain named after him. He knew Sikorsky. Anyway, there's a nice biography by one of his students, and the name of the biography is the Delaunay Peak. That's the title of the paper. It's written by N.P. Dolbile. So this is one of his students who wrote this expository paper. It's in English, fortunately, and it describes his very, very eventful life. Okay, so enough for the history lesson. Let's see what the empty sphere method is. Some of you have already seen it. I mean, the original paper is called La Sphère Vide, the empty sphere. It's really a disk or a ball, but yeah, such as what's happening. So we start with the sphere in, say, Rn. And sphere. And then we say S is empty if the sphere divides R into two components. There's a bounded component, the interior, sometimes called the open ball. If interior contains no lattice points. Yeah, I now just realized I should have said, before I said that, I should have said, let lambda in Rn be a lattice. So you start out with a lattice, right? In fact, what I should say is where we're going is, given a lattice, lambda, what does the empty sphere method tell us? It gives us a partition of Rn so that that each each into tetrahedra, into polyhedra. Okay, but these are nice polyhedra, of course, right? These are going to be del and A. So S is empty if it contains no lattice points for the given lattice. And then we're going to say that an empty sphere is maximal if S contains the sphere itself, the boundary of the ball contains greater than or equal to n plus 1 points. Now, reason for this is, well, it can't, it's, once you have n plus 1 points in Rn, you can now talk about the convex hull. And I'll call PS the convex hull. So given a maximal sphere, I'll take PS to be a convex hull. Yeah?
The radius is infinity.
Yeah, but this is on the boundary. Yeah, so S is a sphere. So
oh, a sphere.
Yeah. You know, I was thinking about nothing in the interior. You know, the way we would write a modern situation is we'd write as balls. We'd talk about this empty ball method, but Delaunay said empty sphere, so I'm just going to go with it. Yeah. So for example, if you have 3 points in the plane, then you can talk about the circle, and there's a unique circle between those 3 points. So that's the picture. The circle is determined by 3 points. Of course, there could be another point, and this will lead to this notion of special that I'll say in a second. Okay, but just a reminder, I mean, this is in part for the Teichmüller people because there are people who, I mean, yeah, okay, so.
Excuse me.
Yeah.
Audience.
Good.
It's my pen. Oh, it must be
Empty. It has to. Yeah. Maximal is a modifier for empty sphere. Yeah. Okay. So let's suppose we have a lattice, and so what is I want to produce a. So this is a lattice. A lattice is by the way, a subgroup of Rn, so that when you take the quotient, it's compact, right? You get a torus. So that's what I mean by lattice. It's a It's looks like that. That's a two-dimensional version. And I want to create a cell decomposition out of this. And so what I do is I say, well, first step is there exists an empty sphere. Okay, so, and that's pretty clear because this is a discrete set, so I can just choose some set like that and take it's a closed set, so I can take, there's an empty sphere. And then secondly, there exists a maximal sphere. Now this requires a little algorithm. And Delaunay's algorithm is as follows. The first thing you do is, well, let's put it here. So we take that point where we had the empty sphere, that point's not in the lattice, and we grow that thing until it bumps up against a point there. Right? And then basically the next step is so that gets me 1 point. And then Delaunay says, well, then we look at maybe we can take a hyperplane this way or a line this way, and we can push away from that. And so we can make, and we keep pushing, and we keep pushing, and we do that. And so that gives us in this case, a circle with 2 points. In this case, in 2D, I need to get to 3 points. So the next thing to do is I take these 3 points, and then I look, I could go either left or right. I can look to this side or the other side, but eventually I'm going to end up with my thing. So that's the algorithm he gives. Has anyone coded this? No? coded it. Huh? Well, you get a choice. You can, whichever way you want. So it's a good point. So in fact, one of the reasons I wanted to bring up this construction is because, you know, in the time of Delaunay, and his teachers would have taught him this, and this was taught in all universities at the time, is that if you had a picture like this, or these are supposed to be circles. This is a point, and this is a point, and I look at all circles that pass through those 2 points, right? And it's in fact, it's sort of a compact family of circles because you can add in the circle that goes straight up and down, right? So you get this whole loop of circles in the space of circles. And what is this classically called? Who knows? A pencil. Very good. Who is that? Yeah? This is a pencil of circles. So, you know, if you were if you were a student in the 19th century, that was like what you do in instead of freshman calculus, you do this. So that's and so what we're doing here at this point is once we get to this, we just move in the pencil of circles and to butt up against another point. Now, because it's a lattice and it has finite covolume or it's co-compact, you're going to hit a lattice point. You're going to eventually, in this pencil, you will eventually hit something else. And so this is the Delaunay construction. Okay. Okay, and yeah, so what do I want to say next? And then then there's a little bit more. To get the next circle, what do you do? Well, suppose you've already constructed one circle. So I've constructed this circle. To get my tetrahedron or my polyhedron, I take the convex hull. That gives me my PS. Right. The maximal sphere is here. That's my PS. To get the next one, what Delaunay says is basically you apply the pencil of circles argument again. You say, well, it's an open-closed argument, basically. Suppose this point or whatever point is not in your tetrahedron or in your triangle. Then you should free up the maximal. You should look at the pencil through these two things, which are on the face. So you basically look at the union of the faces you've already created. You look at in the boundary, and then you look at that. And if you don't have this covered yet, what you do is you free up and look at the pencil of circles here. And eventually you'll hit something. And so that'll get you the new thing, right? And then the Delaunay condition follows automatically, and everyone knows the Delaunay condition, which is simply that that each polyhedron, when you take it's circumscribed by some sphere or by some circle, and it's empty. It doesn't contain any other vertices or any other of your finite point set. Okay. Any questions about that? So that's what Delaunay does. He does it in like 2 pages. Notice one thing he doesn't say. He doesn't say anything about Voronoi. A lot of people just say, okay, Delaunay, I first have to do my Voronoi, then I take the dual. But there's no reason to do that. You just do Delaunay right away, right? And yeah, in fact, so this paper was in honor of Voronoi. It was submitted to some proceedings that was in honor of Voronoi. The argument was given so that apparently he was trying to find a shortcut in some big tome of Voronoi, and by using this construction, he was able to simplify a lot of Voronoi arguments. But he doesn't use Voronoi. He doesn't use the Voronoi. Okay, so that's the Delaunay. Now, what he does mention in his right, that's too far. Right. So right after making the construction, he talks about special lattices. see, most of the time when you take a generic lattice, you actually will get just triangles. But then there are some special ones, special situations. For example, if you just take a rectangular lattice or the square lattice, then when you apply the algorithm, the maximal circles will be not containing just 3 points, they'll contain 4. Right? And so, and you can also look, it happens in other lattices. I could look at this lattice, and then I draw that. By lattice, I mean the natural extension, right? And so there are situations where you have more than 3 points, or in general, more than n plus 1 points in dimensions. So, yeah. And also note it, yeah, so there, yeah, maybe I shouldn't say that first. I'll say something else first. Maybe I will leave that there. Oh. Yeah, if there are any questions, please don't hesitate to stop me. Yeah, of course. Right. Not from the lattice. From in n equals 2, not from the lattice. Right, good point. Yeah. But let me point out that like the people in lattices were just the beginning, because then people started looking at finite point sets. So thank you for the question. You just look at a finite point set, and what's most important is just basically discrete, and you can apply the same method. You don't have to have a lattice. And in this case, you could have a situation where you can have 5, for example. But with a lattice, you're much more constricted. Yeah, there is some question about what happens if this is the finite point set. Well, and what happens out there? Well, you know, it's not so important, because you only wanted to triangulate a certain finite part of the plane, and you were able to do so. Yeah. But yeah, thank you. Right. So special lattices. So special lattices lead to tessellations. And so let me try to explain this a little bit. So it's basically an observation by, as far as I understand, this is an observation of William Veitch. Maybe, I don't know exactly when, 1990s, in the 1990s probably. And yeah. Any questions? Okay. Okay. So if you look at the set of special marked lattices, these things map nicely. There's a natural map to the Ferry tessellation. So the Ferry tessellation of the hyperbolic plane is maybe the nicest one. So it's basically the tessellation with 0 shear everywhere, right? So and this is, I said hyperbolic plane, and I do mean plane, but it's just nicer to draw it this way. The real line is here. I've compactified the real line like that, and I guess I'm going around this way maybe, so maybe this should be -1 and this should be 1. And so the real line, and then you get all the rationals by continuing in this process, right? So that's the Ferry tessellation. And so I need to explain, what do I mean by the natural map? And what do I mean by marked? So, right. So marked lattices so we're going to take a V and a W inside R2, and maybe I want the determinant of VW, thinking of these as column vectors, as positive. They're oriented, right? And then you can look at a marked lattice, which is simply a lattice with a choice of basis. So n lambda VW is m times V1, V2 plus m times V2, W1, W2, and then m, n, and z. And then the thing to notice is that GL2R, this is the 2 by 2 matrices with determinant not equal to 0, right? These are the invertible matrices and 2 by 2 invertible matrices. This acts on the set of marked lattices in a natural way. And the action is, in this case, it's transitive and it's faithful. So, so what I mean to say is that basically this action gives you an identification, right? Because the 2 by 2 matrices act on vectors like this by matrix multiplication. And you can get from any lattice any other lattice by acting by one of these. Right? Now, on the other hand, you know, you can think of, is there? Oh, I should use this. This is cool. Is that too much? No. Oh, I should have a thing, a little squeegee thing. No, that's so unfun. That's. No, I want to do it this way. Okay. 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 Okay, so that's that. And now I have to worry about the stuff. Okay. Okay. So anyway, so the point is that when we want to care about what the delineation triangulation looks like, or the Delaunay partition looks like, you know, if we rescale the lattice, if we just rescale, we zoom in, then we basically see the same thing. There's no difference between two things, right? And also, if I rotate the lattice, what's a maximal sphere is still a maximal sphere, so that doesn't change. So I really don't care up to rotation or homothety. And so when I take GL2R, so I've identified, by this action I can identify GL2R with the lattices, but I don't care if the lattice is up to scaling or if I don't care about rotation, then I can mod out by scaling, which is lambda times the identity matrix, where lambda's in the reals without 0. And then on the other hand, I have SO2, or O2. I don't really care. Well, I guess I took out the O2 because, and then, okay, so now is the question for the, so who's a geometer? Okay, if you're a geometer, you can't answer this question. What is this? You're not a geometer, what is this? Not quite. It's almost the modular curve. Okay, geometers. Did I make a mistake? What is this? It's the hyperbolic plane, no? I mean, you guys are used to seeing it this way, SL2R modulo SO2, right? But when I mod out by the rescaling, it's the same thing, right? I can reduce down to determinant 1 for the on the right. Right? So this thing is the hyperbolic plane. Okay? So in some sense, the space of lattices, the geometers should know this already, the space of lattices up to rotation and up to homothety, that's the hyperbolic plane. So marked lattices. Okay? Now, right. Okay. Now what about or in other words, the tori, the flat tori up to isometry, that's the hyperbolic plane. They're marked tori, right? They're not marked, if they're not marked, then it's the modular curve. But I'm marking my guys. Yeah. Okay, so what is the special guys? So that makes sense of this. Now how do I get, so given a special marked lattice, I can obtain a point in the hyperbolic plane. Because I just look at I look at the equivalence class of marked lattices up to rotation and rescaling, and that gives me a point in the hyperbolic plane. So I get a map here. Okay? And what I'm saying is that the image of that map, the image of the special marked guys, the special ones, is exactly the fairy tessellation. So for example, here, that's on the one skeleton. What I mean is on the one skeleton, that's a place where you might see a 4 points. Okay. So you have a lattice where all the points, where the things are like this. And then you have this. Right, so it's like a rectangular lattice, basically. Right? In a rectangular lattice, these are the ones. But the rectangular lattices can be shifted, they can be stretched, and so this is what you see. Okay, so there is an interesting thing. What happens when you go across from here to here, across that line? What are the other things? Well, if you go in one direction, what you're doing is you're taking your 4 points, and one thing you can do is sort of move a little bit to a new 4 points. And when you do that, this circle breaks up into 2 circles. So you'll have one that now looks like this, and then one that looks like that. So there's a bifurcation occurring, right? And if you go the other direction, you get a different bifurcation. In particular, what happens is you have this, there's your polyhedron associated to the special guy. And when you go one way, you'll end up with a picture like this for the new. And on the other way, you get something like that. And so naturally, when you go from this side to this side, you go flip. You do a flip move. Okay, so flipping here corresponds to moving from one cell to the other. In particular, all of these guys in this particular triangle all have the same Delaunay partition. They all look the same. And when you move a little bit over here, you change it. I mean, ultimately, it may not look that different, but you're doing a flip. And then you can flip again, and you get a new region. You flip again, you get a new thing. So you can see as you move in the space of lattices how the triangulation changes. In particular, these special marked lattices, the terminology that was finally, I think, settled on is that these are iso-Delaunay. So in particular, this is the iso-Delaunay tessellation of the hyperbolic plane. Okay, so that's, okay. Any questions so far? Oh. Right. Great question. I mean, Yeah, so there the geometry on the right-hand side will now be SL and R modulo SON. And I don't know really what happens, what it looks like. But yeah, so that's part of my advertising here is that this is this construction is very well not understood very well at all. I think there's just a couple people. There's Veach, there's me and my co-author. There is Samuel Friedman, whose work thought about and Joshua Bowman. But yeah, no, it's a very beautiful thing, and not many people have actually been working on it. So that's one of the reasons I wanted to speak about it, is to advertise. Lots of open questions. Okay. Right. So I want to explain a little bit about how to think about this. So here's a little bit of mind-bending stuff. So far, everything has been quite pleasant. It's a good afternoon. We're having bouillabaisse. So let me... yeah, so instead of thinking about changing the lattice, I would rather, which is the same as changing the flat torus, I would rather stick with the same torus and change the geometry of the torus. So, or in other words, I want to stick with the same lattice. Let's just look at there's my lattice. I'm not going to change that. However, I'm going to change the geometry of it. How am I going to change it? Well, it's Euclidean geometry, and Euclidean geometry is determined by the ball. So this is the ball of radius 1. So once I tell you what the ball of radius 1 is, you can translate it around, you can move it around, you can expand it. We know what the geometry is once I tell you that's the Euclidean ball. Okay, it's supposed to be a translation invariant geometry. But instead of tilting my lattice, what I'm going to do is tilt my quadratic form. So I now look at ellipse. So now I have an ellipse, and that's going to be the ball of radius 1. A little weird, but this distance is supposed to be 1, and this distance is supposed to be 1, and that distance is supposed to be 1. So doing that is equivalent to actually, it's dual in a sense to actually moving the lattice. So instead of thinking about a tilted lattice, I could think about now a tilted geometry. So like a maximal sphere might look like that now. There's my maximal sphere. It's now an ellipse in that geometry. And so the space of ellipses is essentially the hyperbolic plane. GL2R acts transitively, blah, 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 blah. And so that's how this is working, right? This is like, okay, looks like something from Lie groups or something hard. But we're taking the space of ellipses is thinking of it as the hyperbolic plane. And here's the cool, I mean, when trying to understand Veach's paper, I was having difficulty. So maybe I shouldn't do that again. You did give me an eraser. What did I do with it? Oh, I put it over here. When I was trying to figure out Veach's paper, I realized the following lemma, which says, if you have a pencil of ellipses through 4 points, that corresponds to a geodesic in the hyperbolic plane. Okay? So just under this map, what I just said, these ellipses you take, so by a pencil ellipse was 3 points, so ellipse is determined by 5 points. So if you have 1 point free, you have 1 degree of freedom, right? And so here's an example. Here's an ellipse. Here's an ellipse. Right? And there's a whole bunch of them that that go through there. And so there's a whole family of ellipses, and that corresponds to a geodesic in H2. And it turns, so when you fix your lattice, you're fixing these 4 points. And as you change your geometry, you're just changing the ellipse. So I see a family of ellipses as I change the geometry of my torus. And so that's so this corresponds. So this is a little bit of projective geometry to prove this. I'm not going to prove it here, but that's the idea. Okay. So yeah, I haven't even told you what a translation structure is. Yeah, so I need to say what a translation structure is. And because, so the question is, can this be generalized to other situations? And the answer is yes in the case of translation structures. So if you, flat tori, their generalization, their natural generalization, for which there's an SL2R action, is the set of translation surfaces. And so, and many of you already know what it is, so I'm not going to, I'm sorry for those of you who did not raise your hand, please. But I was going to give a demonstration of a construction of one, but here I'll just give the definition. So basically it's just like what Vincent said the other day, is you take a bunch of polygons, and it could be multiple polygons in the plane. So these are polygons in the plane. And what you require is that any two polygons, well, there's a matching between the edges of the different polygons. So for example, this is matched with this. Okay? And so there's an edge matching. And you want to make sure that the normal vectors are pointing in the opposite directions in the plane. So they're parallel edges. But it's also that their outward normal is pointing in the opposite direction. So it's a pairing of all the edges like this. And then identify this edge with that edge. And when I do it by translation. That's the whole point, is that I basically pick this polygon up and I stick it right there. Right. So when you flow, you're flowing in a straight line. So I flow here, and I flow across, and then I flow into the other side. So if you need some intuition about what, I mean, we've already seen asteroids. I think we saw Jeff play the asteroids video in the torus. It's the same thing, right? The torus is a translation surface, or flat torus. The only issue here now is that there's an additional thing you can have is these cone points. You can have singularities that correspond to places where you have a vertex. I mean, one classical example is this one. You just take this one polygon, you identify this edge with this edge with that edge, this edge with that edge, and this edge with that edge, and you end up with some cone points. And this ends up being genus 2, that when you make all the identifications with one cone point, and the angle of that cone point is 6 pi. Okay? I was going to do another, since I'm running out of time, I don't have time to do it, but one can take any polyhedron so that the cone angle at the vertices of the polyhedron are multiples of 2 pi, rational multiples of 2 pi, and you can unfold that surface, take a branch cover if you like, and form one of these. So in some sense, you can understand the surface, the polyhedron, by understanding the translation surface. So if you're interested in polyhedra in R3, you can understand their geometry by understanding translation surfaces. Up to, you have to make sure that the cone angle is a rational multiple of 2 pi, but that's a dense thing. So if you're a computer scientist, choose the best guy for you, right? It's okay. So they live everywhere. You can find them. I'm not sure I know of any animal species that have translation structures on them, but who knows? Okay, but what's important about them in terms of this problem that I've been discussing here is that there's an SL2R action. That is, given that polygon up there and that polygon there, and I glue them together in a certain way, because the gluings are done by translation, there's a notion of an affine, there's an affine structure, and I can just sort of tilt one to the other. Just like if I take this guy and I apply a matrix like, I guess it's this one. Is that right? So if I apply this to 1, 0, it's going to be 1, 0. Yeah. So if I apply this one, I'll end up with something like this. But notice that because it was done by it was in a GL2R, this matrix, I can still identify. Before the identification was like this, now the identification is like this, and I get a new translation surface. Topologically, it's the same surface, still a genus 2 surface. It just has a different structure. But on the other hand, what I can do is instead of thinking about a tilted translation surface like this one, I can instead look on this one and look at a different geometry. Right? So I'm going to fix this underlying set. And I change, I have the notion of using that geometry on this set, or I can use this geometry, or I can use that geometry. Given any ellipse, I determine a Euclidean geometry. And so you get the same kind of map that Veach was interested in. So Veach recognized this was true, and he proved that you have a nice map from translation surfaces to tessellations. And these are tessellations by, finite area polygons in hyperbolic plane. They have finite area, they're like, usually they're compact, but sometimes they have cusps, etc. And so Veach recognized this, and in fact he proved that basically, he started with he was interested in certain kinds of tessellations that occurred. And he said that if you got a tessellation that consisted of triangles, so that the tiles had exactly 2 cusps. Each tile has exactly 2 cusps. Then back over on this side, he could reconstruct the surface. So he could reconstruct the surface, and in particular, it was this surface was tiled by Euclidean regular polygons. And I should say that n has to be bigger than or equal to 4, I believe, for this. Or maybe, yeah. There's some small n that for which it doesn't work. So he was able to reconstruct, say that the only way you get a tessellation that has exactly 2 cusps in its, like here we have, these are cusps, right? This is an ideal triangle, so there's 3 cusps. But something with only 2 cusps would look like maybe something like this. There's 2 cusps. Right? So if you had something with just 2 cusps, it had to be tiled by Euclidean polygons, which is pretty rare in translation surface world. Most translation surfaces are not tiled by n-gons, regular n-gons. Okay, so so let me get to, so that's part of the reconstruction problem. So what I said is that step 4 here, whichever erase, said that you can reconstruct can you reconstruct the translation surface from a tessellation? So there's a reconstruction problem. Given the tessellation, can you do this? And the answer is, in this case, yes. And then there's a conjecture. The conjecture in general is you can always do it. Now there is a little caveat here because you get the same you get the same tessellation if the translation surfaces differ by a cover. If one is a cover of another. So the real question is, does the tessellation determine the universal cover? That's enough. Okay, so does the tessellation of, and so I'm out of time basically, but our theorem is almost. Yeah. So the question is, does tessellation determine a surface, translation surface, up to universal cover, up to covering or covering? And the answer is almost. Almost, yes. What we have to do is add a little bit more data to the tessellation. We have a decorated tessellation, finite amount of data at each vertex. In fact, the set from which it's drawn, the data is drawn, is finite. It's not that it's a finite amount of data, it's just that at each point in the tessellation, we have to have a little bit more. It's actually, yeah. And given that, we can do it. But in general, it's open. I mean, in general, the question, it's still open. I hope someone will actually, some smart person will be able to answer it. So, maybe, yeah. Thanks very much. Yeah.